So today we're starting chapter 2 on matrices. And a matrix is just a rectangular array of numbers. Or a rectangular array of scalars. And an m by n matrix has m rows. M is always the number of rows, the first number, and n columns. So for example, if we take A to be 1, 2, 3, 4, 5, 6, there are m equal 2 rows and n equal 3 columns. If you take the matrix B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, for example, this is a 4 by 3 matrix. This A was a 2 by 3 matrix. Because the number of rows is 4, and the number of columns is 3. And in fact, you can think of a vector in Rn. So a column vector in Rn is also a matrix with just one column. It's an n by 1 matrix, n rows, 1 column. And there is a so the general notation for a matrix, an m by n matrix A, say, we write the coordinates, the entries, aij. So A11, A12 up to A1n, they're n columns. Second row, A21, A22 up to 2n, A2n. Down to the nth row, AM1, AM2 up to AMN. In fact, this is exactly the same sort of notation we used when we were looking at m linear equations in n variables, and we used the aij's for the coordinates. So this is an m by n matrix, and the jth column of A, you just look at their n columns, you look at the jth. So this would be A1j, A2j down to AMJ. So the jth column of this matrix A is, let's write it as column sub j of A. It's just this m-dimensional column vector, A1j, A2j, A3j, down to AMJ. In each row, you're taking the coordinate in the jth column. That's the jth column of A. And the ith row of A, you look at the ith row, row sub I of A. So let's say here we have the ith row. The coordinates are AI1, AI2, up to AIM. So the ith row of A is an n-dimensional row vector, AI1, AI2, AI3, up to AIN. What you might call the zero matrix Z, the m by n zero matrix ZMN. It's just the matrix where all the coefficients, all the coordinates are zero. And it's an m by n matrix, but everything in it is zero. So there is a simple algebra of matrices. So addition of matrices. So just as with vectors, if you're looking at coordinate vectors, you only can add vectors of the same dimension. You can only add matrices of the same shape. So this is addition of m by n matrices as follows. Suppose A is the matrix with coordinates aij, and B is the matrix with coordinates bij. So the number of rows in both cases is m, and the number of columns in both cases is n. You take the sum just by adding the coordinates. So for example, if A is the matrix 2, -3, 0, 1, 5, 2, and B is the matrix 0, 3, 19, 7, -8, 1. So these are both matrices with 2 rows and 3 columns. So these are 2 by 3 matrices. And if you add them, you add coordinates. 2 plus 0 is 2. -3 plus 3 is 0. 0 plus 19 is 19. 1 plus 7 is 8. 5 minus 8 is -3. 2 plus 1 is 3. So this is the sum of the matrices. And you can scale or multiply a matrix. If this is the matrix A with coordinates aij, C times A just means multiply every coordinate by C. So for example, if this is A, what is 7 times A? You multiply everything by 7. 14 minus 21, 0. 7, 35, 14. So we have, so this is scalar multiplication. So we have addition of matrices and scalar multiplication. And with these operations, the set of all m by n matrices is a vector space. You can add and subtract matrices, and you can multiply matrices by scalars. Right? Notice if you take any matrix A and multiply it by the scalar 1, you just get A. And if you take any matrix A and multiply it by scalar 0, you get the 0 matrix. Which I was writing at the ZMN. And then it is, of course, straightforward as a calculation to check that these operations have the, or matrices have the following properties. So matrix addition and matrix scalar multiplication satisfy the following properties. You have associativity. You take two matrices A and B and add them, and then add C to the result. That's the same as adding A to B plus C. And it's commutative. That means that A plus B equals B plus A. And there's an identity matrix. Take A plus the 0 matrix. These are n by n matrices. You just get back A. And there's an additive inverse. A plus minus A is always the 0 matrix. Let me just give an example of that. If A is 2, 3, minus 1, 5, 0, 7, and you let A be the negative of that, or minus A, be minus 1 times A. So you're just multiplying every coordinate by minus 1. That means changing the sign. Minus 2, minus 3, 1, minus 5, 0, plus 1. If you add A plus minus A, you get 0, 0, 0, 0, 0, 0. Get the 0 matrix. In this case, the 2 by 3 0 matrix. And scalar multiplication satisfies the following simple properties also. If you take two scalars, C and C prime, if you take A and multiply it by C prime, and then multiply that by C, that's the same as C prime times A. And then you have the two distributive laws. C times the sum of two matrices is CA plus CB, and C plus C prime times A is CA plus C prime times A. So because addition of matrices and scalar multiplication of matrices satisfy these properties, it's a vector space. The set of all matrices of a fixed shape is a vector space. That's just interesting to know. Now, there's another operation on matrices which is very important. We'll see why later. And it's called the transpose of a matrix. So you obtain the transpose of a matrix by interchanging the rows and the columns. So what I mean by that's the following. A is the matrix 1, 2, 3, 4, 5, 6. This is a 2 by 3 matrix. The transpose, which I'll denote by a superscript T, this is going to be, instead of 2 by 3, 3 by 2. So the first row of A, 1, 2, 3, becomes the first column of the transpose. The second row of A, 4, 5, 6, becomes the second column of the transpose. So it's like you're flipping the matrix around. And you can notice, if you repeat that, this is another matrix. What's the transpose of the transpose? This will be 2 by 3 again. The first row becomes the first column. The second row becomes the second column. The third row becomes the third column. And you're back to what you got, A. So this is sort of a general rule about transposes. If you double transpose a matrix, you recover the original matrix. Mm-hmm. Now, we added matrices and we multiplied matrices by scalars, but sometimes, not always, but sometimes it's possible to multiply matrices. So this is matrix multiplication. And it's not the case multiplication. It's not the case that you can multiply matrices that have the same shape. In fact, if you take a 2 by 3 matrix and another 2 by 3 matrix, it's not possible to multiply them. When is it possible to multiply them? So suppose that A is an M by N matrix, and B is an N by P matrix. So A has M rows and N columns. B has N rows and P columns. The important thing is that A and B, the number of columns in A equals the number of rows in B. And when that's the case, then you can multiply. So you can multiply two matrices A and B if the number of columns of A equals the number of rows in B. And the idea is if A is an M by N matrix, so here's the ith row, AI1, AI2, up to AIN. And B is an N by P matrix. So here is the ith column, A1I, A B1I, B2I, down to BNI. Sorry, this is the jth column. B1J, B2J, down to BNJ. So this row has n numbers, and this column has n numbers. And the way you multiply the row and the column, so I want AB to be a matrix C with coefficients Cij. And you get the coefficient Cij in the product matrix by multiplying this row into this column, and you do that by multiplying the corresponding coordinates and adding. So this would be AI1B1J plus AI2B2J all the way down to AINBNJ. Or in sigma notation, this is the sum. K goes from 1 up to n, AIKBKJ. So that's the formula for matrix multiplication. And it looks complicated, but it's a lot easier when you just start to do it. So suppose I take the matrix, I don't know, 1, 2, 3, 4, and the matrix 5, 6, 7, 8. So this is my matrix A, and this is my matrix B. So this is a 2 by 2 matrix, and this is a 2 by 2 matrix. And the product's going to be a 2 by 2 matrix. So you have to plug numbers into all four places, 2 in the first row, 2 in the second row. So when you multiply the first row into the first column, that's sort of 1, 2 times 5, 7. That's going to be, when you multiply the corresponding coordinates and add 1 times 5 plus 2 times 7, that's 19. You get a 19 here. Here, this is the first row, second column. You take the first row of A, you multiply it by the second column of B. This is 1 times 6 plus 2 times 8, 6 plus 16, this is 22. For the second row, first column, you take the second row of A and multiply it by the first column of B. That's 3 times 5 plus 4 times 7, which is 15 plus 28 is 43. And for the second row, second column coordinate, the second row of A times the second column of B is 3 times 6 plus 4 times 8, 18 plus 32 is 60. So this is the product, this matrix. In general, if A is an M by N matrix and B is an N by P matrix, the product, let's call it C, it's like the N's cancel, will be an M by P matrix. So 2 by 2 times 2 by 2 is 2 by 2. Let's look at another example. Suppose A is the matrix 1, 2, 3, 4, 5, 6. So this is 3 by 2. And B, let's say, is a 2 by 2 matrix. I'll make it 2 by 3. That means 2 rows, 3 columns. 0, 2, minus 1, 5, minus 4, 2. So 3 by 2 times 2 by 3, if A, B equals C, C will be a 3 times 3 matrix, right? 3 times 2, 2 times 3, the 2's cancel, you get 3 by 3. What is the matrix C? You multiply the first, to get the first row, this is going to be a 3 by 3 matrix. So the entry in the first row, first column, you multiply the first row by the first column, you get 0 plus 10. First row, second column, you get 2 minus 8. First row, third column, you get 3. Second row, first column, second row into the first column, 0 plus 20. Second row, second column, 6 minus 16. Second row, third column, minus 3 plus 8 is 5. Third row into the first column is 30. Third row times the second column, 10 minus 24 is minus 14. Third row, third column is minus 5 plus 12 is 7. So A times B, this is the product matrix C. Now notice this is C is equal to AB. What about BA? BA, so B is 2 by 3, A is 3 by 2, so the product is going to be 2 by 2. So if you're multiplying B times A, it's first row into the first column. Let me write this. Let me just actually write down. So B times A is 0, 2 minus 1, 5 minus 4, 2. And A is 1, 2, 3, 4, 5, 6. So to get the first element, the first row, first column element, multiply the first row into the first column, you get 0 plus 6 minus 5. First row into the second column, 0 plus 8 minus 6 is 2. Second row into the first column, 5 minus 12 plus 10 is 15 minus 12 is 3. Second row, second column entry, the second row into the second column is 10 minus 16 plus 12. 10 plus 12 is 22. minus 16 is 6. So if I did my arithmetic right, this is B times A. It's a 2 by 2 matrix. And if you look at this, you see that even though AB and BA are defined, they're completely different matrices. They don't even have the same dimensions. They don't have the same number of rows and columns. So and this is a very important fact. Even when you have like the simplest case, suppose A and B are 2 by 2 matrices. So AB and BA are also 2 by 2 matrices. Let's compute an example. So maybe AB is 2, 5, 3, 8. And B is minus 1, 7. Make this minus 3, 7, minus 2, 5. So these are 2 by 2 matrices. What is A times B? So first row, so it's going to be a 2 by 2 matrix. First row into first column, minus 6 minus 10 is minus 16. First row, second column, 14 plus 25, 37. Second row, first column, minus 9 minus 16 is minus 25. Second row, second column is 21 plus 40 is 61. So that's what the matrix AB is. Suppose we write BA, we calculate BA. So B minus 3, 7, minus 2, 5, A 2, 5, 3, 8. What is that? So first row, first column, minus 6 plus 21 is 15. Second row, first row, second column, minus 15 plus 56, 56 minus 15 is 41. Second row, first column, minus 4 plus 15 is 11. Second row, second column, minus 10 plus 40 is 30. So this is BA. And you notice they're completely different matrices. AB is not equal to BA. This just emphasizes the fact that matrix multiplication, even for 2 by 2 matrices, is not commutative. Let's look at a very special case. Suppose I take the matrix A, which is 2, 5, 3, 8, and I multiply it by a column vector, let's say 1 minus 2. So this is a 2 by 2 matrix. A column vector, again, you can think of as a matrix. There are 2 rows and 1 column. So the result will be a 2 by 1 matrix, another column vector. So the first coordinate, take the first row into the only column, the first column. 2 minus 10 is minus 8. Second row, first column. 3 minus 16 is minus 13. So this matrix times this column vector gives another column vector. Or if I take 2, 5, 3, 8, and I multiply it on the left by a row vector, say 1 minus 2. So this is a 1 by 2 matrix. This is a 2 by 2 matrix. The result will be a 1 by 2 matrix, something that looks like that. So first row, first column is 2 minus 6 is minus 4. First row, second column is 5 minus 16 is minus 11. So when we do this matrix multiplication on the left by a column vector, by a row vector, we get another row vector. When we multiply the matrix on the right by a column vector, we get another column vector. Again, let me emphasize the rule for the shape of a matrix that comes from matrix multiplication. If you have an m by n matrix and you multiply it by an n by p matrix, so the number of columns equals the number of rows, so you can perform matrix multiplication, the result is an m by p matrix. It's like the n's cancel. So this is a very, very, very important relation. Now, matrix multiplication, when it's possible, satisfies very nice properties also. So let's look at some properties of matrix multiplication. So suppose A is an m by n matrix and B and C are n by p matrices. So B and C, let me say it differently. Suppose A is an n by n matrix, B is an n by p matrix, and C is a p by q matrix. So A and B, A has the number of columns equals the number of columns of A equals the number of rows of B. So you can multiply AB, and this is an M by P matrix. But C has P columns. So I can take this and multiply it by C, and the result, because this is P by Q, the result will be an M by Q matrix. On the other hand, if I look at B and C, B is N by P, C is P by Q, so this product is defined, and it's an N by Q matrix. And I can multiply that on the left by A, which is an M by N matrix. So the result, M by N times N by Q, is M by Q. So these two matrices have the same dimensions, and in fact, they're always equal. So A, when multiplication is defined, matrix multiplication is defined, AB times C is A times BC. So this is the statement of associativity of matrix multiplication. So how can we prove this? So if A has coordinates Aij, and B has coordinates Bjk, and C has coordinates, say, CKL, when I multiply AB, and I want to find, let's say, the ikth coordinate of the multi-matrix AB, that summation, J goes from 1 up to N, Aij, Bjk, that's the ik coordinate of AB. So if I take AB times C, and I want, let's say, the i-th coordinate of this. This is the sum of the i-kth coordinate of AB times the k-lth coordinate of C. This is the sum of ik. This is sum for k going from 1 up to n. The ik coordinate of AB, which is this. So this is summation. K goes from 1 up to n. AB sub ik is summation. J goes from 1 up to n. Aij, bjk, ckl. And if I interchange the summations, this is summation, j goes from 1 up to n. Summation, k goes from 1 up to n. Let me just double check that everything is right here. This is an m by n. This is n by p. This is p by q. So AB, the ik coordinate of AB is the sum of aij, bjk. J goes from 1 up to n. And I runs from 1 up to m. And k goes from 1 up to q. If I take AB times C, and I want to take the i-th coordinate of that, I goes from 1 up to m. L, that's the number of columns in the matrix C. L goes from 1 let's see, AB sub ik. I goes from 1 to m, k goes from 1 to p. And IL, I goes from 1 to m, and L goes from 1 to q. So if I interchange coordinates, so AB sub IL is summation K goes from 1 to P. That's what it is. K goes from 1 to P. J goes from 1 to N. K goes from 1 to P. Aij, bjk, ckl. The aij doesn't depend on k, so I can write this as summation. J goes from 1 up to n. Aij, summation k goes from 1 up to p. Bjk, ckl. But this coordinate is simply in the matrix BC, the JLth coordinate. Then this is exactly A times BC, the ILth coordinate, which is what we wanted to show. Okay, so that is a proof that matrix multiplication is associative. It's a little bit technical, but all the details are not just on the paper I just did, but in the textbook as well. What are some other properties of matrix multiplication? Suppose I take the n by n identity matrix, IN. So what is this matrix? It's a square matrix. Square means the number of rows equals the number of columns. Down the main diagonal, you have zero, you have ones, and everything else is zero. So this is the 4x4 identity matrix. And if A is any m by n matrix, the identity times A is A, and A times the identity is A. So there's an identity matrix that has that property. We also have distributive laws. If I take A times the sum of two matrices, this is A times B plus A times C. And in the opposite way, also, because matrix multiplication is not commutative. A plus B times C is always AC plus BC. And we have, if you take C times the product AB, that's exactly the same as multiplying A first by C and then multiplying by B, or A times CB. So these are all properties of matrix multiplication. And all the usual properties of matrix multiplication should follow if you have a matrix A and multiply. So A to the power K means you multiply A by itself K times. And A to the K times A to the L is A to the K plus L. So the usual rules of exponents hold. Now, a very important special case is for square matrices. A matrix is square if the number of rows equals the number of columns. So 2 by 2. That's a square matrix. Or 3 by 3. So these are square matrices. And you can always multiply a 2 by 2 by a 2 by 2 matrix, or a 3 by 3 by a 3 by 3 matrix. And for every n, the set of n by n matrices has well-defined addition and multiplication. And in the language of algebra, the square matrices of any fixed size form what's called a ring. But that's not so important for us now. But you can't define matrix polynomials. So A to the K, so for K positive integer, this is just multiplying A by itself K times. And we define A to the power 0 to be the identity matrix. So if you have a polynomial like P of x equals 2x squared minus 3x plus 5, we can define, so we can also think of this as 2x squared minus 3x to the first power plus 5 times x to the 0. We can define the polynomial evaluated at a as 2 times a squared minus 3 times a plus 5 times the identity. You're substituting a for x. So for example, suppose we take p of x equal to 2x squared plus 3x plus 5, or minus 3x was my example. 2x squared minus 3x plus 5. And we let A be the matrix 1, 2, 3, 4. What is A squared? A squared means A times A. That's 1, 2, 3, 4 times 1, 2, 3, 4. What do you get? Row into column. 1 plus 6 is 7. 2 plus 8 is 10. 3 plus 12 is 15. 6 plus 16 is 22. So a squared is this. So what is P of A? It's 2a squared minus 3a plus 5 times the identity. So we just calculated a squared, 7, 10, 15, 22, minus 3 times a, 1, 2, 3, 4, plus 5 times the identity, 1, 0, 0, 1. So when we put this all together, let's see, what is this? This is 14, 20, 30, 42, minus 3 times this, 3, 6, 9, 12, plus 5 times the identity, 5, 0, 0, 5. So when we add coordinates, we get what? 14 minus 3 is 11, plus 5 is 16. 20 minus 6 is 14, plus 0 is 14. 30 minus 9 is 21, plus 0 is 21. And (42 minus 12 is 30, plus 5 is 35. So when we evaluate this polynomial, this quadratic polynomial at A, we get this matrix. Now, an n by n matrix is said to be invertible, matrix A, if there exists a matrix B, n by n, such that AB is the identity and BA is the identity. Right? And see, let's find an example of an invertible matrix. So suppose A to be 2, 5, 1, 3. I claim I let B be 3 minus 5 minus 1, 2. This is an inverse. So let's calculate AB. 2, 5, 1, 3. 3 minus 5 minus 1, 2. So this is 6 minus 5 is 1. Minus 10 plus 10 is 0. 3 minus 3 is 0. Minus 5 plus 6 is 1. So for this A and this B, A times B is the 2 by 2 identity matrix. And what is BA? Again, B is 3 minus 5 minus 1, 2. And A is 2, 5, 1, 3. I get 6 minus 5 is 1. 15 minus 15 is 0. Minus 2 plus 2 is 0. Minus 5 plus 6 is 1. So A and B are inverses of each other. A times B and B times A are both equal to the identity. And in fact, just as with many other situations, the inverse of a matrix is unique. So that A be an n by n matrix and B and C n by n matrices. Suppose B and C are both inverses of A. Suppose AB and BA are equal to the identity, and AC times CA and AC and CA are both equal to the identity. Then what can I say about B? B is B times the identity. I can write the identity as A times C. By associativity, this is BA times C. BA is the identity, so this is the identity times C, which is C. So if A has both a left and a right inverse, or if A has two inverses, they in fact have to be equal to each other. Let's go back and look at the transpose. Remember, the transpose of the m by n matrix, A, with coordinates aij, is the matrix A transpose, which will be an n times n matrix. And the ijth component of the transpose, aijt, will just be aji. This is the coefficient in the original matrix. And I claim the following very interesting property of transposes. If I take AB and I transpose it, so what is that? Let's say A is m by n, B is n by p. So the product is m by p. And when I transpose it, it's going to be p by m. Suppose I take B transpose times A transpose. A transpose is n by m. B transpose is p by n. So this matrix is also going to be a p by m matrix. And I claim they're equal. So taking the transpose is sort of order reversing for a product. The transpose of A times B is B transpose times A transpose. Let's try and prove that. So A is m by n, B is n by p. So when you multiply them, the product is going to be m by p. And B transpose, if B is n by p, B transpose is p by n. And A transpose is n by p. So B transpose times A transpose is a p by m matrix. AB is m by p, so AB transpose is p by m. And so the fact about transposes of products says that the transpose of a product is sort of order reversing. The transpose of AB is B transpose times A transpose. So let's see how we can prove that. So suppose AB transpose, let's call that, suppose we let AB equals C, which is going to have coordinates Cij. So AB transpose is C transpose. The coordinates are what you get when you reverse Cij, Cji. So in the jth row, ith column, this is the coordinate. What is Cji, Cij? Cij is summation Aik Bkj. K goes from 1 up to n. This is Cji transpose, which is C. The ijth component, sorry. Yeah, the ijth component of AB is CT. That's the ijth component. When you take the transpose, the ijth component of the transpose is the jith component of the original product. So if AB is C, AB transpose is C transpose. Its coordinates are the ijth coordinate of the transpose is the jith coordinate of the original matrix. So for the transpose, the ijth component of the transpose is the jith component of the original matrix. So the ijth component of AB, like AB transpose, the ijth component of that is just the ijth component of the product transpose, which is the jith component of C, which is summation K goes from 1 up to n, A sub jk, B sub ki, which is summation K goes from 1 up to n. B sub ki is B sub ik transpose. A sub jk is A sub kj transpose. So this is simply exactly the ijth component. If I take B transpose, A transpose, this is the ijth component. So this says that the transpose of AB is the product of B transpose, A transpose. And that was what I wanted to prove in this case. I should add one thing, which is almost high school algebra, certainly pre-calculus. If A is the matrix A, B, C, D, what's called the determinant of A is simply the number AD minus BC. So if AD minus BC is 1, then the inverse of A always exists. It's the matrix D minus B minus CD. That's the inverse of A. And what is the proof? I take AB, or A times this A inverse, A, B, C, D, D minus B minus CA, I get AD minus BC minus AB plus AB is 0. CD minus CD is 0. Minus B plus AD or AD minus BC. So this is the scale where AD minus BC times the vector 1, 0, 0, 1, or AD minus BC, the determinant of A, times the 2 by 2 identity matrix. So if the determinant of A is 1, this is just the identity. And if the determinant of A is any non-zero number, then A inverse will be 1 over the determinant times this basic matrix minus B minus C AD. So this gives you a formula for the inverse of a 2 by 2 matrix. In general, to find the inverse of a matrix is hard. For example, if we take A to be 1, 2, 3, 4, the determinant of A is 1 times 4 minus 2 times 3. 4 minus 6 is minus 2. So I can define A inverse to be the reciprocal of the determinant, 1 over minus 2 or minus a half, times the matrix 4 minus 2 minus 3, 1. So if I do my scalar multiplication, this is minus 2 plus 1, 3 halves minus a half. Let's check and see if this is the inverse. 1, 2, 3, 4 times minus 2, 1, 3 halves minus a half. Let's see, that's minus 2 plus 3 is 1. 1 minus 1 is 0. Minus 6 plus 6 is 0. 3 minus 2 is 1. So that checks. And also you can check this is minus 2, 1, 3 halves minus a half, times 1, 2, 3, 4. So that's the basic rule for the inverse of a 2 by 2 matrix. Okay. So tomorrow I will show you how to use matrices to very efficiently solve a system of homogeneous or inhomogeneous linear equations. And that is a very powerful tool in algebra. All right, well, so chapter 2, I think, is not going to be, well, I shouldn't say it, it's not going to be on the exam on Thursday, but we are moving through chapter 2 right now, and you worked hard and keep up. Any questions before we stop for the morning?
Professor, can you help me?
Yes.
Okay, so you did the homework yesterday or day before yesterday in chapter 1, section 1.6, and exercise number 5. I got a different answer. Can you check again, please?
Okay. So
Chapter 1, section 1.6, number 5.
section 1.6, number 5. So number 5 says to find two representations of the vector 7 minus 3, 2
Mhm.
as say C1 times 5 minus 2, 1 plus C2, 1 minus 2, 5 plus C3, 1, 1 minus 4.
You
So you
said
want to find
yeah.
that.
You said the scalars, C1, C2, C3 is 1, 1, 1, but I got different.
No. So, so you misunderstand something. There are infinitely many different solutions to this problem.
Oh, you just give them the
Infinitely
one.
many.
Okay.
I gave two particular ones. You probably found a different one,
Yeah.
right?
Mhm.
But there are infinitely many correct answers. Of course, there are also infinitely many incorrect answers, but there are infinitely many correct answers. And if your answer is correct, that's all that matters. It doesn't matter what particular solutions I found.
I just solved for 3 equations.
Okay.
Mhm.
Then you did it correctly. And does your answer work?
Yeah. Yes.
Okay, well, then it's correct.
Okay.
Okay.
Yeah.
It's like saying, pick a number. Well, I pick 7. Maybe you pick 100. Is one of us wrong? No, we each picked a number.
Yeah, I know many solutions. Yeah. Mhm.
Yeah.
So just found the two solution is
Yeah.
enough. Mhm.
Yeah.
Okay.
I want
Thank
just
you.
to emphasize that if the vectors are not linearly independent, so those 3 vectors are not linearly independent, then you no longer have a unique representation as a linear combination of those vectors.
Mhm. Okay, thank you. You have children today, tomorrow, or
Yes,
today? Uh,
I have an office hour at 7 o'clock tonight and also at 7 o'clock tomorrow night.
okay. See you then. Thank you so much.
Okay, very good. Any other questions before we go? No, okay. All right. That's all for today then. I'll be back tomorrow at 9. Bye all.